Bueno, chavales, ¿qué pasa, tíos? Estamos aquí en otro vídeo más de FS2020, ok, de lo que ha subido la empresa, ¿vale? La empresa. Hoy toca ver lo de Aerodinamicas, ok. Grabé un vídeo anterior, lo que no se me ha grabado a vos. Y nada, decía que para grabar en el campo utilizo este micro casero, ok, de moto. Pero nada, vamos a ello. Los subtítulos están en español, ok. Episodio 3, Aerodinamicos.
Hi, I'm Sebastian Bloch, CEO of Asobo Studio, and today we're going to talk about aerodynamics. When we started working on Microsoft Flight Simulator, we first studied all the code that has been written on Flight Simulator X. There's been many years of work on all the code base, and the code base of the simulation of the aerodynamics was pretty huge. I will cover 5 areas of improvements that we made to the Flight Simulator aerodynamics and physics. First, we made improvements to the core simulation engine. Second, we made improvements to the actual simulations of the different systems of the aircraft. Then the biggest area we reworked was the aerodynamics. We reworked the aerodynamics simulation from scratch in the simulator. I'm going to go over the details of how the aerodynamics simulation now works. One big area that we reworked was the weather system. The biggest interaction of the aircraft is with the air. It's the air that makes the aircraft fly. And so we reworked how the air was simulated in the world. We're creating a full simulation of the airflow over the planet, and I'm going to explain how the airflow interacts with the world, the environment, and also with the weather.
Dice, improved core or physics engines, o sea, la física del motor.
The core of the simulation is a better collision model with the environment. So the system now supports sloped surfaces, which means that aircraft can land on sloped runways. But also on any
pistas inclinadas, eso es lo que decía.
If you want to simulate engine failure, you can make a cross-country landing on any surface, including sloped surfaces like fields on mountain slopes. It's gonna work anywhere. To make sloped surfaces work, we have to rewrite the friction model of the aircraft.
Vale, han puesto más sistema de fricción.
Dynamic friction, static friction. All the friction parameters have been improved, and so like the rubber now really behaves on all different surfaces like tarmac, cement.
El caucho ahora se comporta realmente en toda la rueda, o sea que el caucho es más real.
Exactly like they showed with realistic
Scaving, friction, bueno, un montón de cosas.
The way the bumps on the ground are handled, they are now
Bumps.
realistically simulated, and the way the brakes are simulated. So this allows for planes to come to a full stop even on slopes, and that's when they transition from dynamic friction to static friction, and planes can really come to a complete halt exactly as they should on slopes. So when you do a landing on a sloped runway, you can now roll and you can stop on the slope, turn around and take off again. We also rewrote the integration system of the simulation. So the integrator is what makes the simulation go forward. It calculates all the states of the system. So one thing we changed is now that the simulation is running at a much higher frame rate.
Integrado.
So it adapts to the
More steps per second.
Your monitor. This means
Adaptive time step.
Whatever the frame rate of your display, even if you have slower frame rates, frames are exactly going to match the display. And also the simulation is always going to run at a higher frame rate. So even if your frame rate goes down, the simulation stays at a high frame rate and you don't lose anything of the realism. Planes always behave as they should, whatever the frame rate. Another big change we made to the integrator is the way the integration now works is much more realistic, and it has removed one artifact that was present in previous versions of Flight Simulator.
El facto que estaba presente en versiones anteriores. Viejo integrado se resistió a resistir el cambio.
It was forcing planes to always move more or less in a straight line. So the integration is now super realistic. It's exactly moving the aircraft as
está moviendo exactamente el avión como deberían. No se sienten en los rails, o sea que antes se sentían como si pilotásemos entre dos rails. Un rail y dos rails. Y el avión está aquí en medio.
Feels more real, and planes, when they rotate, when they yaw, when they pitch, when they roll, they feel much more realistic now as they travel through air.
Se siente mucho más realista. Rewriting, o sea, reescripción en los sistemas del avión.
In the simulation, other than aerodynamics, we improved the factor simulation, which also improved the way the ball.
Mejoramos el sistema de factor de carga. Vale, por la bola esta de aquí.
Vale,
¿veis? El avión se mueve y la bola también.
easily because it reacts much more realistically than before. And so we have now specific.
No tenemos un consumo especificado de combustible.
Which is matching the actual POH of the aircraft.
Coincide con la POF.
Flaps can be set in the files, which allows to have more control.
Mejora de flaps.
We work the way gears and external parts like external tanks are simulated. Instead of just hard coding the moments they apply on the aircraft, they are actually physical elements in the
físicas. Las físicas de los elementos más reales, donde deberían, como deberían. Humedad real del aire, el hielo.
Around the aircraft, and because the weather system is now accurate and simulated volumetrically, if you fly through clouds, you're going to get a different icing than if you fly through dry air. And so this is now simulated in 3D volumetrically. Also what we did is the legacy simulation code from Flight Simulator X is still available. So you can switch to the legacy simulation if you don't like the new simulation. We don't want to force anyone to move to the new simulation. So all aircrafts have been reviewed with
by profesionales, o sea que profesionales han hecho la review.
Which were already matching POH when we presented them, but to make sure they actually are controlled exactly like they should. There's many parameters that we set that are not actually present in POH, such as how fast the aircraft is going to roll when you move the yoke to the left, for example, depending on your airspeed. This is data that is not always available, but that professional pilots feel. They know how agile the plane is at what speed, and so these are parameters that we set with them. And we reviewed the whole aircraft to make, for example, stalls as they should be, or if an aircraft can spin or not, or the way basically they behave so that they don't just match performance parameters from the POH, but actually feel as the real aircraft when you fly them in real life. So the big change we made to the system is the aerodynamic simulation has been reworked. So how we simulate now is much more advanced. So we subdivide the aircraft into thousands of surfaces which are mapped over the airframe.
10,000 superficies de aire. O sea, flipar.
Over the tail. There's thousands of little surfaces which are placed exactly where they should over the geometry of the aircraft.
Sobre la geometría del avión, o sea, se colocan donde debería.
It's going to have its own air pressure, its own humidity. This means that the right wing, for example, can fly through a cloud where the left wing doesn't, and you can have different wind, turbulence and humidity on the right wing. Each of these surfaces has a realistic airflow simulation. Each surface is going to have its own wind direction, its own air pressure, and it's going to do a full three-dimensional calculation to compute what is the force and moment that should result from the airflow flying over the surface. This simulation includes the airflow speed and detachment and orientation. It will realistically simulate stall. The stall is when the airflow is actually too far by the surface, and the airflow cannot stay attached to the air surface anymore. So this is now simulated surface by surface, which means that we can have a left wing stalling, especially because of the weather and the full realistic simulation of each surface in the world. But each surface will also deflect the airflow. The airflow is going to be impacted, and surfaces which are behind are going to get a different airflow because the airflow was impacted by the surfaces in front. So this, for example, is going to allow more aerobatics. So for example, the airflow is coming from the propeller and is hitting the tail. And that's how you can, for example, enter into a flat spin or some of the figures. So for example, when you can do an inverted spin, that's because the propeller hits the tail. This is now realistically simulated.
The improvement
we made to the simulation is the simulation of the air mass. We now simulate the air mass globally over the entire planet and realistically. Every area of the world has its own simulation of air. And we know where the air is flowing everywhere on the planet, and this then feeds into the aerodynamic system of the surfaces of the aircraft. So this means that, for example, we will have volumetric clouds, which you can see in the world.
Nubes volumétricas también.
On TCUs, on towering cumulus clouds.
TCU.
Usually it's a kind of cloud which exists because there's a lot of updraft of air. But when they get really big, there's an updraft on the side, and in the middle it actually goes down. That's basically why they're so dangerous, and you should never in a small aircraft get close to a TCU. In a big aircraft you're going to get a lot of turbulence, and so this is now simulated the airflow in the world is going to match the clouds and it's going to fly. The air is going to move up and down inside of the clouds. So you will see a video which is going to show this airflow. So in order to visualize the airflow, we released thousands of particles in the world and displayed the trajectory of the particles. They just do exactly the same calculations than the aircraft in the world. So each particle samples the world atmosphere, exactly like each surface on the aircraft. So you can see on clouds that the air is moving up and down. You can see the turbulences, which is when the airflow of the particles changes color and the particles move more randomly. So these are like wind shear or turbulences.
Wind shear.
Go up because it's in the middle of the cloud.
Wind shear son nubes como, son ráfagas de viento como un grifo, o sea, bajan, pero luego se esparcen.
In the world which match actually the weather. So this air mass simulation also works with the world shape, like the shape of the world, which can depend on buildings, hills, forests, mountains, valleys. So all these different shapes worldwide are going to influence the airflow in the world. So for example, the air flows over a stadium or a hill. It's going to create updraft, so the wind is going to flow up. And on the other side, usually it goes back down, but in a turbulent way, right? It has to go back down, but it's gonna be creating a lot of rolling turbulences. So you can imagine when you fly over this air with the aircraft, if the aircraft is flying slow, if it's a small aircraft, it's gonna get all these rolling moments, it's gonna get the up and down draft, and you're gonna feel all these bumps. So on the video you're going to see there's, for example, wind flowing over mountains, and it naturally creates turbulences. On the other side, in the valleys where the currents come together, they collide and it creates these turbulences. You can see in the middle of the valley, you can see the up and down draft, and you can see how the slope of the wind is actually very, very steep, right? It goes along the slope. So this is it for the improvements on the aerodynamics, on the physics. So we improved the core simulation, we improved many of the simulated systems.
Yo no sé cómo pueden hacer esto, en serio, pero
with the surface-based system,
espectacular.
we reworked the simulation of the airflow in the world. All these changes come together to create a much more realistic simulation of the aircraft. Aircrafts are now simulated realistically to the performance data that is available. They fly exactly to the real-world performance, but they also feel exactly like real aircraft. They turn, they behave when you move this yoke exactly like a real aircraft, and they fly through the world. They fly through the air exactly like a real aircraft flies through the air in the real world, being impacted by clouds, by mountains, by buildings, by the shape of the world, right? I hope you enjoyed the details I gave about the simulation, about what we changed. Thank you for your time. Please subscribe to the Alpha, and talk to you soon.
Buenas tardes. Bueno, tío, espero que os haya gustado este vídeo, y nos vemos en el próximo.